Thank you so much, Martin, for that, for the introduction, for the invitation. It's my great pleasure to be here. And I did my PhD pretty close to Hollywood, so allow me to start with a movie, which is not mine at all, but in fact, just a television advertisement. And in fact, the television advertisement of the first industrial robot ever. The manufacturer Unimate back then got so cocky that in the moment where they released the first industrial robot, just 2 or 3 years later, they went on air and said, okay, we'll have a robot made at home. We'll soon have, well, this monster, like you will be laughing, obviously, at home and or something based on it, and it will solve, well, basically all the different household problems. And the amazing thing is, I mean, when you think about it, this was 1969 when they aired it. And the robot programming back then actually has changed very, very, very little. Society has changed a lot. Computing has changed a lot. Even our robots look much, much better. But actually, in fact, how we endow robots with the ability to accomplish tasks has changed surprisingly little. Now, this video goes on for another 1.5 minutes. I'll save you the rest. And we really have to ask ourselves the question, why don't we have such robots? And that conversely comes with the, well, equivalent question of, so where have you been successful with the robotics? And there's an obvious answer. Well, for example, in car industry, where, well, accuracies of 150 millimeters matter, where we do the same thing over and over again so that we execute the same task, well, thousands of times for a very, very high price, and we don't need to reprogram the robot all the time. Similarly, anybody who's bought either a lawnmower or a vacuumer robot has been very disappointed for the lawnmower because you had to typically put a wire into the grass, and for the, well, for the vacuuming robot, because you had to completely rearrange your furniture such that the robot would actually be able to operate. And then it would do some randomized strategy of banging against all your furniture all the time. So what did we basically do? Well, we typically adapted the task until it finally fit the robot instead of, well, adapting the robot to the task. Now, that obviously is totally coherent with the analytical robotics worldview. And when I got into robot learning back in the, well, around the year 2000, that was the dominant point of view. And it was simply, you were, in fact, when I told people I wanted to do learning, they told me, you're a fool. Robotics just needs 3 components. First of all, an accurate forward model. And that is, well, basically just a physics simulator. And of course, physical principles are fantastic, right? They give us a really good generalization. But unfortunately, well, all models are wrong, but some are useful. In fact, you have a lot of non-linearities in unmodelable situations when it comes to contact, when it comes to friction, when it comes to actuator dynamics, and even when it comes to, well, high-speed decision making, unless you have completely sensed everything away. The second thing they basically said back then was, well, the next thing you need is a good planning algorithm, nothing else. And unfortunately, well, we know planning isn't actually that easy. See, you have to have an exponential explosion of situations. Replanning is hard, and you have, well, all kinds of optimization biases where the planner exploits the faults of the model in order to give you a plan not really optimized for the scenario. And finally, you needed to have good fast feedback control, which is basically an error killer, but unfortunately, it also requires that you build the best bodies for control. And, well, these are stiff, power-hungry, complex design robots. Now, not at all what we would like to have when we look at humans as a comparison, or dogs, or any other animal, which are typically not stiff, not power hungry. Your whole body runs on 100 watts in between 100 watts and 300 watts. That's basically nothing by comparison. And, well, find the design is fairly complex, so also quite different. Then basically in the last 5 years, we have seen that the world rapidly changed, or actually, especially in the last 5 years, we've seen it, but the change happened already quite a bit before it. And we went to the complete opposite extreme of the pendulum. In fact, we went to a deep learning, end-to-end learning point of view, which basically said, oh, we don't need anything from the classical robotics point of view. In fact, a highly flexible representation with suitable algorithms, aka a deep net, is everything you need. But the problem is, when you can learn everything, that also means it is very, very easy to learn something which is physically implausible. A small error can cause a gigantic optimization bias. And anybody who's actually really used a deep net for, well, in conjunction with a, well, interesting robot, well, typically had to fight some form of a huge optimization bias. And, well, unless they killed their robot, they haven't done an interesting, at least once, they have actually not done an interesting task. And then, well, at some point, you really want to have insight into your solution. So just being black box doesn't give you any safety guarantees. It actually puts you into a very limited situation. The next part, of course, of the worldview now dominant is loads of data. But the problem is robots live in real time. So we get basically few episodes, very, very few episodes, and episodes are what you need for learning. And at the same time, you get a fast state action stream, which you have to evaluate in real time online. Real world obviously means also real damages. Anybody who hasn't broken his robot hasn't actually worked with the robot. And breaking it means typically it looks perfect in simulation. And the worst is, you get the answer now whenever you talk to people about the problem of loads of data, that physics simulators are all we need as data generators. But that is back to square one. If we can simulate physics well enough that a physics simulator is all we need, well, planning solves the problem. You don't need learning if you have a physics simulator which is good enough to give you the data you need for planning. Even if it is just planning under uncertainty, which considers the scenario approach with many sampled versions, you only need learning if you're really, well, if you're really beyond your physics simulator. And finally, well, the deep learning gospel says lots of computation. And, well, lots of computation, but obviously makes many things impossible. So like online learning, or what do you do if your robot can't communicate in time with a big cluster? Or what do you do about energy storage if you want to learn on the real system? And you recognize, actually, by overswinging, we've already driven the car against the wall. And that is not the right approach either. Now, obviously, I'm not going to tell you what the right approach is, but I can give you a few lessons which we have learned in, well, by now, well, more than a decade of robot learning in my lab. And, well, that is, how should robot learning differ? And first of all, if you don't do learning on the real system, you haven't actually learned anything about your learning algorithm. It's really, really important for, if you want to apply learning, that you manage to adapt online without replanning. And then finally, well, you really want to be able to adapt online without replanning, avoid real-time bottlenecks, and you want to cope with this really big problem of having very, very few episodes, while at the same time actually learn from a giant stream of data. On the long run, you need to be partially explainable, because otherwise you can never give guarantees for, like, let's say, a surgery robot or a robot in the streets. And, well, physical plausibility is key when you do learning. So just an unstructured net may not be enough. Finally, when you really want to bring in simulations, you have to figure out how to cope with the simulation optimization bias, or SOB, and build the best bodies, not just the best bodies for feedback control. So really, it's really quite fundamentally how you should differ from what's happening in the core simulation or a big data set. Well, now obviously I don't have all the answers, but I can tell you at least a few of my lessons, and therefore I'll focus basically now on just 4 of these lessons. How can we learn from a real system from very little data? Then subsequently on how we can learn modular policies, how we can create physically plausible deep models. And well, if I still have time, I'll tell you a little bit about, well, why and how we should build the best bodies and for learning and learn on the real system. So this is both the research questions as well as the outline for the remainder of this talk. Unfortunately, I'm way too slow today. So let's start with the learning. Well, obviously you want to do imitation learning, and imitation learning, in fact, has a very long history already. In fact, the earliest where you can find it is in the work of Michie and Chambers, and all the algorithms which came subsequently, whether it was Claude Salmond, it basically just boiled down to maximizing policy similarity or minimizing the difference between two policies. And that is well known as model-based, model-free behavioral cloning. Now you can, of course, bring in a model, and surprisingly, up to Peter Englert, I don't think anybody had ever done this in the case of imitation learning, where people, instead of doing model-based behavioral cloning, typically focused on the dual problem of inverse reinforcement learning. However, if you want to do the dual problem, you're actually making your life harder. So in order to solve the dual problem effectively, you need to put in something which is smart. Like, for example, put in just minimal physics, in which case you only get a optimal parametric policy class like motor primitives. Because if you're using the complete dual problem, well, in this case, inverse reinforcement learning actually becomes harder than model-based behavioral cloning. If, on the other hand, you put in minimal physics, well, you actually get very effective learning systems. And let me show you two examples here. This here was a ball bouncing task, and it has a ball on a string, and well, that's why it's actually so fast. And surprisingly, when you want to hack this task up, it is really, really hard. We've had generations of students who try to do it just by hacking, actually fail at doing this task, simply because of the variability in the different hard to model linearities, which are all time variant, which are all slightly problematic. On the other hand, the strategy learned by imitation learning worked out of the box, which was pretty nice. And you can do similar, you can learn actually more complex things. So for example, you could also learn forehand movements in over a certain domain in robotic table tennis. This work done by Sebastian Gomez Gonzalez, one of my PhD students. Now, imitation is obviously not enough. So instead, typically, we also have the objective of reinforcement learning. And reinforcement learning is, when you think about it, well, it replaces the log of the two distributions just by a generic reward function. And by that, it actually has a big problem, since by that, it uses its embedding in the data. And obviously, you can bring in the same constraints about the physics system. And this would give you, for example, reinforcement learning by linear programming, a standard approach, and which again comes with a dual. Or you could alternatively use Bellman's principle of optimality in order to obtain a backward recursion, which we in reinforcement learning, for some bizarre reason, called the Bellman equation. Bellman, I don't think, ever claimed it because it was known long before him already. Now, Puterman very nicely puts it, the primal is again harder than the dual, and it's not, and both of these approaches suffer from a major issue, since there is no natural way of bringing data into them. Now, the one thing which we realized already more than 10 years ago, and which has still been driving many algorithms, not just ours, also behind TRPO and SAC and many others, is the simple insight that policy similarity is in fact the objective of behavioral cloning, is a really important constraint, or you can also put it into the cost function as SAC does, which you want to bring into which you want to bring into your reinforcement learning problem. If you do this, you obtain, depending on your choice of Q, so Q can be both the past data, but it can also be an approximation of the past data, or you can even replace it by something more crazy as people in, well, like the uniform distribution as people do in entropy regularized reinforcement learning, which builds on it. All of this yields different analytical solutions and mellow and softmax formulations, entropy regularizations, and even natural policy gradients in TRPO are just its approximations. So this is actually quite a big generalizing step for us. And we directly made it work in robotics. And well, here you see basically first how it looked after an imitation. And the imitation fails. Now, I'll let you see the rest of it. So basically, this algorithm in that early formulation managed to get the ball into the cup for the first time around 40 trials, and it became perfect after 90 trials. Now, what did we in the end have here? Well, we actually had learned, well, quite a good policy, which manages to be faster, but with a lower acceleration than the human, which was the key bottleneck in the human behavior and why it couldn't be transferred to the robot, but by imitation learning. And at the same time, it had to learn the complete hand-eye coordination along with during that task. Now, we obviously asked ourselves if now that algorithm is now a few years old, and we asked ourselves, well, what is if you would just take our formulation again, and we compared with everything else there is, how competitive are we? And it turned out when you take the task of robot juggling, it's actually still the state of the art. And so still, if you want to learn on a high-speed system, that is still in the year 2021, the best way of doing things. In fact, so good that when I saw this one-handed juggling on the same day where we took that movie, I asked my student Kai Plöger, hey, Kai, what about two-handed juggling? I came next morning, I got this video. You can actually learn two-handed juggling just as well as one-handed juggling. And well, it's actually quite straightforward to do this with little data if you just bring in the minimal amount of physical insights. Now, obviously, now I realize I've been going way too slow. I'll skip one part, the part about comprehensible modular policies, which is dear to my heart, but maybe a bit more interesting for you guys right now is actually the part about how we can learn to execute and how we can learn to execute safely with a deep neural network. And for that, we asked ourselves the question of how can we learn physically plausible deep models? And for that, you got to recognize, of course, the key thing you need if you want to bring learning in a model-based, if you want to bring a model-based learning, so any simulator-based learning, anything which creates a simulator for you, or uses a model to a robot, well, then you actually have to bring in more insights. And getting a physics simulator, well, is typically not enough. Instead, well, when you want to use models for execution, well, you can use them all over, right? They give you very, very good initial policies, whether you use them for inverse model, an energy model, or a forward model. And it's typically one thing which you need to talk about when you're talking to engineers, since in the end, model learning is absolute. Model learning gives you one form of plausibility. In classical engineering, well, what do people do in robotics? They typically completely take the robot apart. They identify all the parameters, measure everything, and well, they actually get quite a bad solution considering the effort. But it's a solution which generalizes well. It just has all the kinks when it comes to actuator dynamics, friction, and so on. Then you could do system identification, in which case you need for a robot system at least the length and the orientations of the kinematic structure. In that case, you get the perfect, well, physics features. The only problem that they are over-parameterized. And again, you can compute a model from it. However, because it's over-parameterized, you may get awfully wrong. And then, of course, you could do what everybody's doing these days. Oh, well, let's just learn a black box model and ignore physics altogether. And annoyingly, this doesn't even give you an energy model, which is something we very frequently need if you want to learn complex tasks. My PhD student, Michael Luther, came actually up with a very amazing idea, the so-called deep Lagrangian neural networks, which, well, kicked off this whole craze on Hamiltonian Lagrangian neural networks. And they guaranteed that you get physically plausible models by constraining the model with a sensible physical parameter. And physical plausibility in this context means that every model parameter configuration is in fact a mechanical system. Amazingly, it allows you to learn with a deep neural network, not only forward and inverse models, which are, well, kind of obvious to train, but also energy models. And well, so all of the three model kinds you need for control. Now, the amazing part about the energy model is that you get this indirectly. You can use all the different forms of cost in order to optimize this output by using this right form of a model representation. This, with a resulting DLAN approach, can learn the force decomposition completely unsupervised. So you can actually look at the motor torques, the inertia components, the Coriolis and centrifugal forces, as well as the gravity as separate components. And it's kind of cool when you watch how different control looks in here. Now, obviously, the analytical model is getting to the solution relatively fast because this is a very, very well-tuned analytical model. And you need to imagine the eigenfrequency of these things are terrible because there's a pendulum of finger length. It's so close to the sensor delays, to the sensor sampling frequency. It's actually quite hard. It's much harder than the regular simulated task. The system identification actually fails altogether because it never gets to excite the right behavior. And well, DLAN manages to learn nearly as fast as the analytical model takes for just control knowing the perfect model. Now, Michael also showed that this is very useful for robot control and that you can get a very high performance, better than manufacturer performance out of our Barrett WAM. Now let's talk quickly about bodies. And well, we really want to have good bodies, since classical robotics just builds the best body, well, which you can apply and control with classical approaches. When you look at these human examples, they're far beyond, right? Humans learn without braking, they learn at high velocities, and they perform very skillful motions. So with other words, human performance robot learning needs better bodies. And one thing, well, we started together with Dieter Büchler, one of my PhD students, who's now he's a group leader at Max Planck, and since he graduated last year. And we basically focused on, well, creating a high acceleration robot with small moving masses so that it's more or less human-like, but also completely uncontrollable by classical methods. So in fact, we had Neville Hogan and we showed it to him and he said, well, you know, this looks like a computer scientist's wet dream, but it's a control engineer's nightmare. And I really like that statement. And well, in the end, we have antagonistic actuation, just like a human arm, which prevents damages to the robot and also enables compliance just as much as high E forces. And we really build it for performance and learning and not for control. Now here you see a hitting movement. The system itself manages to do really high accelerations, much higher than our Barrett WAM. And well, you can actually use it even for training from scratch. And unfortunately, of course, you have to train with a simulated ball, pre-train with a simulated ball, where simulated means you're replaying past trajectories and you're just looking at geometric interception. And well, fast forward, after 2 hours, you can actually see halfway sensible strategies evolving. If you're after 14 hours, it hits the simulated ball quite well. In fact, so well that the physics simulator prescribes that it should work. Now, you need another 30 minutes of training on a real ball, but then you actually get pretty good performance. And well, I get to finish on actually pretty much on time. Unfortunately, I had to skip the really important part about learning comprehensible modular policies. But I think I have good lessons for you. Well, first of all, learn on the real system. And learning on the real system means you have to consider 3 different options. The first option is, well, start with imitation, then do reinforcement learning. That gives you high learning speed. If you want to do model learning, well, you have to actually figure out safe model learning for safe model-based RL. And that is an unsolved question up to now. I could tell you that, never mind. Then you really, if you want to do long-term learning without imitation before, well, in this case, you have to actually build bodies which are suitable for learning from scratch and kick out classical robot building. And you want to adapt online. So that basically also means you have to actually figure out how to have parameterized policies that generalize, and that typically requires that you that you actually have more than just a local interpolation resulting from a black box, but you have to actually bring in some form of physics in order to get movement primitives or something of the like. And well, I didn't talk about how to avoid the real-time bottleneck using modularity and how we can cope with the little episodic data problem, or the, well, at least being partially explainable. But I did talk about, well, being physically plausible, for which you need DLAN, and how to build the best bodies for learning with small moving masses, antagonistic variable stiffness actuation, and robot learning. For that, let me just say, robot learning should really be at the center of 3 fields. We should take things from cognitive science and human motor control. We need to revolutionize robot engineering. And well, we as a group at least try to also heavily interact with the machine learning itself. These are just some of the many other things we work on. So from reinforcement learning algorithms for robotics, tactile skill libraries, doing better learning control, automating stability proofs, over, well, developing all kinds of new methods from many different perspectives, up to finally, well, looking how this all interacts with humans. With that, I would like to close and hope you have many questions.
Thanks a lot, Jan. This was a very, very impressive presentation. Very, very nice to follow, and thanks a lot. So if there are some questions, please type them in the chat or just unmute yourself and ask them. We'll have time for 1 or 2 questions. I have one right to start. So you showed impressive work of how to teach robots complicated and complex skills and tasks. And referring to the very first video you showed, which was also very nice, actually, how do you think in the future, or in the near future, let's say, would people teach a robot in practice to accomplish such tasks like spreading a bread or helping washing dishes, like from the more user perspective? Do you have any intuition here?
So I think what we will need, I mean, one key thing is that we need to simplify the user interfaces, so that we can actually do teach in or showing of tasks, demonstrations much easier. That's, I think, one key part. One other key part is that we really depend on the cloud in the future, so that all of the tasks which have been previously learned by other robots can already be shared, so that when you show a robot, okay, this is how you spread the butter on a piece of bread, then the first thing is to actually look whether there is a policy which looks similar to the policy which would result from imitation learning, and which has maybe already been pre-trained, so that you could actually try this. This is, I think, one important part. The second important part is, and which, well, was hopefully trained on in a somewhat similar scenario, a similar robot, similar knife, similar type of butter situation. I mean, you know, butter free differently on how cold, depending on how cold it is, it's very different to spread. And so you hopefully have many of these pre-trained policies. I don't think that policies actually generalize so well between situations. So for humans, there's a strong evidence that our policies don't generalize that well. So let me take you a simple example is golf and hockey. Both of them have a, you know, a big swing, and in both cases you want to swing a ball, get a ball really far. It turns out there's near zero generalization between golf and hockey. That somebody who's is good at something totally, well, a very different striking sport learns as fast as a golf player learns hockey. So if you know, like, let's say tennis, it actually gives you as much of an advantage as knowing golf. And that's very surprising, right? When you think about it.
Yeah.
But that evidence is really strong. And so it may well be that we humans learn specific tasks. And that's, I think, yeah, a modular database of tasks is, I think, the key part we need in there.
Yeah, that sounds very, very reasonable. There's one question from Theo Cachet, who is a PhD student at Naval Labs Europe and in Paris, Sorbonne University. Very interesting presentation. Thank you. Very impressive results. From what I understand, the models you developed are single task expert. Did you try to create a multitask model for real robot? If yes, how do you specify the current task to the robot?
So yeah, that was a part which I skipped. So what we really tried, we worked on for 1 decade, is opening the black box and distinguish the single tasks, the primitives, just using a supervisor, and basically come up with both on how to do between task generalization, how to activate tasks, how to superimpose tasks, superposition, since many primitives would just apply to parts of the body, and and how to modulate different primitives. And we actually went then as far as how to parse behavior into libraries, how we would, for example, get a whole table tennis game into a library, how to activate then using a gating network, and how to actually then change the learning system by first introducing options, which wasn't enough, since options unfortunately give you good behavior for table tennis, but unfortunately they also break down when they're actually overlapping. And we actually figured out what you do need is then additional constraints on the gating network in order to force the specialization in multitask learning, as you see symbolized up here. So that was precisely what I skipped, now done in less than a minute.
Very good, thanks a lot, Jan.